Okay, welcome everyone to the first talk at this year's Rutgers Experimental Mathematics Seminar. Our first speaker of the year this week will be the founder of the OAS, Neil Sloane, who will talk to us about some sequences and problems and solutions that have come up in the OAS. Please, go ahead, Neil.
Thank you. So here are the topics I'm going to talk about, and mostly they're going to be problems. I was going to give some details of two solutions to problems, but it was so boring, I thought really you'd rather hear problems rather than solutions any day. So I'm going to start by giving an update on the stepping stones puzzle. This is from 2020, and the problem is that you've got an infinite chessboard, and you have a number of stones, and for the case of A of 2, you have 2 stones marked. One that you can put anywhere you want, and then you can put stones labeled 2, 3, 4, 5, 6. They have to be in order, and you can only put down a stone labeled 2 if the sum of the 8 neighbors around it is 2. So you can put a 2 here. Then you can put a 3 here because the sum of the neighbors around the 3, there's nothing there yet except the 1 and the 2. So you can put a 3 there, and then a 4 and a 5, and you can get up to 16. And 16 is optimal, and that's sequence A337663. And I want to report on recent developments. So Brady and I made a video which appeared in January on YouTube. And one of the first comments came in from Skylark Murphy, who improved the lower bound. A really brilliant idea. I thought many people thought about this, but no one else came up with this idea. So the old lower bound was from Andrew Howroyd, who got a lower bound of 5n minus 4 by placing the stones in a zigzag. So you place a 1 stone here and a 1 stone here, and then you can put a 2 there, and a 3 and a 4 and a 5 and a 6. And if you have cleverly pre-placed a 1 here, then you can put a 7 and 8 and 9 and 10 and 11, and so on. Each time you get to another 1, you can go around it and pick up 5 more stones. And so you place them in a zigzag, and you get 5n minus 4. Skylark Murphy's really brilliant idea was to put them in a straight line. Don't do a zigzag, put them in a straight line, separated. So the ones are on this line, and the separation is 2 blank squares. And you start with an extra 1 stone up here, and then you can put a 2 and a 3 and a 4, and a 5 and a 6 and a 7, and you can go as far as you want in that straight line. Then you go around the corner and come back. And each time you pass a 1 stone going that way, you pick up 3 extra steps, and coming back the other way, you pick up another 3. So you get exactly 6n minus 6. You lose a little bit because of what you lose going around the corner and at the start. But when I was preparing the slide, I told her I was going to mention her work, and she said, had I seen her new bound, which is gets 6n minus 6. It's 6 better, and it's very clever. It goes like this. You put the 1s in a straight line, with the initial 1 separated by 1 square. And then you can go 2, 3, 4, 5, 6. Each time you pass one of these, you pick up 3, and you go around the corner, and you come back, and everything goes smoothly until you get just before the starting 1, and after, which would be 23. You'd want to put a 24. The next stone you have to put down is 24. You want to put it there, but you can't because of this extra 1. You could put a 25 there, but you've got to place the 24 first. Well, she puts it here, and then you can go on 26, 27, 28, and then you'd like to put the 29 there, but you can't. You've got to put the 29 somewhere else, and the 29 goes here. And then you can put the 30 either there or there. And so that gives a lower bound of 5 times 6, so 6n lower bound. Very clever.
Sorry, I'm sorry. I think I see a way to go a little further. If you look at this last configuration here, on the bottom right, you can put a 31 right below the 16.
Here.
And then you can put a 32 right next to the 30. And I think you can hop back and forth a bit here and get further.
No, wait, we've got to put a 31. And
Yes,
we
but below the 16.
no, because we've already got the 17 as well.
Oh,
to worry
I
about.
see. Sorry, my bad.
I agree. It would be very nice, and it's quite likely that with a bit of cleverness, yeah, I think there's a considerable amount of improvement, but I don't think it'll improve the 6. That seems really tricky to beat, the coefficient. So that's the lower bound. And while I was making that slide, I thought to I'm sorry if you already heard me say this, I said to myself, this is like accelerating a rocket. Of course, you would say this isn't rocket science, but maybe it is. And so the constraint is do the same problem, but require that the stones that you place down, 2, 3, 4, 5, and so on, are in a path which is connected, vertex connected. And then how far can you get? And I don't know anything about this. It's just a couple of hours old. Now, as far as upper bounds go, Robert Gabitz had an upper bound. His first upper bound was big O of n log n, which was quite significant because it proved that you couldn't go off to infinity with a fixed number of starting stones. There was a possibility that if you were really clever, instead of putting them in a straight line, you could go around in a spiral that would get bigger and bigger and bigger. Well, that's not possible. It's bounded by order of n log n. But then he improved that to 714n as an upper bound. And then in the past year, there have been many new upper bounds, and the most recent one is Jonathan Waltman, who has got it down to 86n plus 32. And the proof is in a link in the sequence. I haven't checked it. As far as the exact values go, there's no change. We know A of 1 through A of 6. But Al Zimmerman is running a programming competition where the contenders have to improve the lower bounds on A of n for n bigger than or equal to 7. And the competition is running, and he sent me some samples of the results. A of 7 now he knows at least 71. And he says that when the competition ends in November, there's a good chance that people will actually be able to, their proof will have established that some of these are in fact the exact values.
But the results, we can't see what people have tried so far, just their score in the contest, right?
I actually haven't looked at the website.
Okay.
You can certainly see the values, but the constructions, I doubt if they're available yet. All right, so as long as I was talking about the best sequences of the year, why not have an award for the best picture of the year? And so the award for the best picture of the year goes to Scott Shannon for his sequence A355798, which it's a sequence, and it goes like this. This is another version of the stained glass windows work that we were doing last year and the year before. Lars Blomberg, Scott and myself, we looked at various versions of stained glass windows where the problem is to count the cells. How many different panes of glass are there in these windows? But this is one we hadn't looked at. Scott said, what if we take a square? So take an array of squares, like here's a 2x2 array of squares, here's a 3x3. Join each point on an edge to all the opposite points, all the points on the opposite edge, join them like that. So here, this point gets joined to these 3, and so on. And the question is, how many regions are there? How many cells? And he's worked out 40 terms. So here's the sequence, which is A355798. And this 4 is because there are 4 cells here. And there's 24 is because there are 4 facets, 4 regions in this picture, 24 regions in this picture, and so on. So, but we don't have a formula. It would be very nice to have a formula. This is a graph, and it has nodes and edges and regions. And these 3 are related by Euler's formula, and Scott also produced the sequences for the number of vertices and the number of edges for each of these things. All right, are you ready? It's the best picture of the year. We used to have a motto that when we were working on the stained glass windows, that if we can't solve it, we'll make art. And I think Scott's new motto, I don't know if he's listening, is if we can't solve it, make carpets. And it's pretty nice. Here's an enlargement of one corner. You can see the cells are color coded. So green is a hexagonal cell. The triangles are all red, and the quadrilaterals are this tan color, light brown. So that's the best picture of the year. All right. And then, well, I thought it'd be interesting to try to find out, can we do anything about finding formulas for slightly simpler versions? So I took an array, instead of taking an n by n array of squares, take a 2 by n array and join all the points on one edge to all the points on the other edge. So it's kind of a simplified, slightly changed, simplified version. So this is the 2 by n case. And here we've got 6 squares, 2 by 3 squares, and there are 52 cells. And of course that number is even, so divide it by 2 to get the sequence. So that's the 26 in the sequence. And Scott worked out, what was it, 50 terms of this sequence. And I was going to mention this at the end of the talk as part of my list of sequences where it would be nice to have a formula. We have quite a, half a dozen or a dozen with simple definitions where we have 50 or 100 or 500 terms, but no formula. And no formula should exist, one feels. But I moved that to here because Scott observed that if you do a transformation on this sequence and remove the equator, then what happens is that the cells that are split by that line merge. And you can see on each edge here, there are 2. I can hear some noise outside. Robert, can you hear that hissing sound?
I don't think so.
I think it's a hedge trimmer. Okay, it seems to have stopped. Good. Okay. Anyway, so if you remove the equator, these cells merge, and there are 2n of them. So, and what you get is this picture. It's the same thing without the horizontal line. And this is one of the ones we know, because it was in our other paper, the paper, the Rose Windows Part 1 paper, which has appeared. We know a formula for that, and therefore we know a formula for this. But this is rather an unusual transformation of the sequence, to remove a line from the graph. But anyway, it works. And the formula you get when you do that, referring back to our old paper, is actually a very classical formula. It's basically the sum over all pairs I and j of whose GCD is 1 of n plus 1 minus I times n plus 1 minus j. I conjectured that, and Max Alexeyev pointed out that it's, I guess it timed out. This Mac can't, I don't want to connect later.
Let's go again.
I just got this computer back. It was hacked and it's not fully working properly. But anyway, we're back, right? Okay, so Max said you can prove that by mapping it using rational transformation. You can map these nodes onto the nodes of a right triangle. And this is a diagram, a graph that we analyzed in a paper when we were studying teaching sets of two-dimensional threshold functions. And so he had a formula, and that formula gave us a formula for that. And that gives a formula for the problem I was looking at. And I want to mention that this is actually a very interesting thing here. This sequence, which is kind of canonical in some way, appears in many different sequences in the OAIS. I did a search, and there are actually now 9 sequences in the OAIS that are all essentially this sequence. If you call this Z of n, then there's a sequence A290131 is Z of n minus 1 plus n minus 1 squared. It's in the same family. It's the same sequence, essentially. So it's a clump. So I've been looking at clumps of families of essentially identical sequences, and I have half a dozen of them. So this is one more way of trying to bring order into the OAIS. So that took care of my version of Scott's sequence, but the big question remains, is there a formula for his magic carpet sequence? We don't know. All right, let me move on. Augusto Santi's recurrence. This is a really amazing recurrence, just crying out to be understood. And it's related to Reed Kelly's old sequence, which is related to the Narayana cows sequence, which is related to the Fibonacci. So we start off with Fibonacci, you add the 2 previous terms, and you're counting rabbits. Narayana, a couple of hundred years later, is counting cows, according to the model. Each term is the sum of the previous term plus the term 2 back. A of n minus 1 plus A of n minus 3. So there's a characteristic polynomial, you find the root, and that tells you essentially what the nth term is. So that's Narayana, sequence A930, one of the old sequences. Reed Kelly says, let's not just add those two numbers, but let's divide by the GCD. So after, for instance, after we get 1, 1, 1, 2, 3, 4, what's the next term? It should be 2 plus 4, but we're going to divide by the GCD of 2 and 4, which is 2. So we get 6 over 2, which is 3. So that's his sequence. And this is really annoying. It's 10 years old, and we know nothing about it, basically. And I wish somebody would spend some time and clean this up. Anyway, there's the definition. And it goes, you can see how it goes. And you don't see 6, right? Until you get to the 4th row here. So 6 is present. You'd never see 8 and you never see 10, but there's no proof that they're missing. So please, someone come to the rescue. Now, when you plot a sequence, when you click the graph button in the OAIS, you get a plot of the first 200 terms, and you get a plot of a scatter plot of all the terms in the B file, basically. And if necessary, the computer takes logs and shows you a log linear plot. So for Reed Kelly's sequence, it grows exponentially. You can see it taking off. That's 200 terms. If you look at 5,000 terms, it's a straight line, except it's not straight, it wobbles. Why does it wobble? Nobody knows. If you did this for Fibonacci, it would be a dead straight line because the nth term is phi to the n, and the logarithm is just n times a constant. Dead straight line. So the mystery. So what about Augusto Santi's new sequence? So he's working from the Fibonacci model, and he takes the sum. We're going to start not with 1, 1, but with 1, 2. So it's a recurrence. Start with 1, 2. The nth, to get the nth term, you add the 2 previous terms and divide by their GCD, and you add their GCD. So let's do it. We start with 1 and 2. 1 and 2 is 3, and the GCD is 1. So it's 3 plus 1, 1 plus 3. We get 4. 2 and 4. 2 plus 4 is 6. Divide by the GCD, we get 3. 3 plus 2 is 5, and so on. goes like that. And now here's the interesting thing. After 2006 steps, it reaches a number about 10 to the 21, and then it repeats with period 2901 for reasons that I don't think anyone understands. And if you change the initial terms, it appears that what happens is either the sequence blows up, keeps growing forever, or it's periodic with period length either 39, 159, or 2901. And 2901 is 3 times a prime, by the way, in case you were wondering. And 155 is not divisible by 3. So there's no obvious relationship between these 4 numbers. So what is going on? As far as I know, no one in the world knows. Are these the only possible periods? And what's going on? Why that number in particular? Surely this isn't random. And so I looked at what happens if you start with 1, 1. And what you get is, it looks like, this is a picture of Santi's sequence. And here it starts out at 1, and it rises up to 10 to the 20 or so in 2000 steps.
And this pin plot is misleading, right? The actual peak happens about 2000 in.
Yeah, the period starts around where the cursor is, about 200, and then that's the period, and it repeats. Yeah.
If it's eventually bounded, then by the Pizarro principle, there should be a period. So I think it boils down to proving that it's bounded.
Yes, agreed. Yes, if it's bounded. But the question is, why is it bounded? And that has to do with the greatest common divisor. So when you look at what happens if you start with 1, 1, which is what I did here, it was not in the OAIS, this sequence. You begin with 1, 1, and you apply Santi's rule, and you get this sequence. And I can't see that because it's covered up by your faces. I'm going to slide that down a bit. Oh, gosh. Okay. Here's the plot of 200 terms. It goes along, and it immediately hits the exponential growth. And if you look at the, I don't know how many terms are here, I can't see anymore. 1,000. With 1,000 terms, it's still growing, but there are huge wobbles in the sequence. And these wobbles have to do with the greatest common divisor. I was talking to Robert about this, and we were saying that really you have to understand what happens to the greatest common divisor. As long as the GCD of successive terms is bounded, then it's not going to blow up. But if we can, I'm sorry, as long as the GCD doesn't grow too much, it's going to blow up. But in order for it to return, to drop down so it can become a periodic sequence, we need a very large GCD, because that will, when we divide by it, it will drop a lot. Have I said that right? Anyway, the GCD controls everything. All right. Okay, I move on. The next one, the Sisyphus sequence, which is another pretty nice sequence. I wish I could control these. I've got pictures of all you folks, but I don't know how to. I'm going to move them back to where they were over here, but at least they only. I hope you can't see all this flashing around. Okay. So the next topic is the Sisyphus sequence. Okay, so the Sisyphus sequence, it was sent in, it's one of Eric Angelini and Carole Dubois' creations. Many wonderful sequences in the OAIS come from Eric. And this caught a lot of people's imagination. And many of my friends and the OAIS worked on it. But sad to say, we still don't know the answer. And here it is. So the rule is, it's a bit like the Collat's problem in a way. You start with 1. If the number is even, you divide it by 2. And if it's odd, you add the next prime. Okay, so let's do it. We start with 1. 1 is odd, so we add the next prime, and which is the first prime, which is 2. So 1 plus 2 is 3. 3 is odd, so again we add the next prime. So we add the next prime being 3. So 3 plus 3 is 6. That's even. Divide by 2 and we get 3. Now we add the next prime, 5. 3 plus 5 is 8, and that's even. And we divide by 2 repeatedly until we get down to an odd number. 8, 4, 2, 1, then we add 7, then we get 8, 4, 2, 1, we add 11, we get 12, 6, 3, we add 13, we get 16, blah, 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 down to 1, and so on. And it looks like this, 200 terms. Here's a picture Rémi Sigrist made showing where this is, I think, about 30,000 terms. The red dots are terms that came after odd numbers. So when you get an odd number, you add a prime, and they're the big numbers, and they're in this red region. And then you divide by 2 repeatedly, and they're down in the blue until you get to another odd number. So the slope here, I measured it, it's about 7n, 7 times. So A of n on this line is about 7 times n. But in fact, it's almost certain that the slope is log n times a constant, because here's what we know and what we don't know. The big question is, does every number appear? It seems very plausible that it does, but some numbers take a long time to appear. So after 10 to the 9th terms, 36 was missing. And so was 72. Of course, if 72 had been there, 36 would have followed it right away. So that's not a surprise, but 36 was missing. Well, then it turns out, if you go out far enough, 36 appears. You have to go out to this many terms, and it's a chain that descends. This is the big even number, and you divide by 2 about 30, 40 times, and you get down to 36. And you divide by 2 twice more, and you get down to 9. So it's a chain of even numbers, which becomes an odd number at the end of the chain, which is that far out. And then 97 was missing for quite a long time. And Martin Ehrenstein found it. He found a 97 at that many terms, and it's a descending chain that starts there after you've added that prime, and then eventually it drops down to 97. So these numbers take a long time to appear. And Alan Wexler made a very nice conjecture and analysis. He says, look at what happens. Really, you expect every number to appear, because whenever you have an odd number and you add a prime to it, that's an even number. So an up step is always immediately followed by a down step, and that's and then it may or may not be an even number. So you may or may not divide by 2 repeatedly. So on the average, you would expect one more down step. So we expect that every third step will be an up step by the next prime, which will be around prime, the n over 3, the n over third prime. So the sequence will spend a lot of time between prime of n over 3 and 4 times it. And so we expect every number to appear eventually. And I thought this was rather amusing. You could say, all right, when does the nth prime appear for the first time? When does 2 appear for the first time? It appears at the 7th step. When does 3 apply for the third time? at the second step, and so on. When does the 25th prime appear? It appears here at that step. So if you look at the graph of this sequence, and don't take logs, let's look at the standard plot you get. You see essentially a string of zeros, and then a large number, and then more zeros. So we'd like to know more about this sequence. So there were some pretty big numbers there. So not a serious question, but I thought it would be amusing to ask, what's the biggest number of the year? And is it from the Sisyphus sequence that we were just looking at? Well, Augusto Santi's sequence was actually bigger, 10 to the 21 or 10 to the 20. But there's an even bigger new number that came up. Pavel Kropitz found a lower bound on the busy bee for number of 6, BB of 6. He showed it's at least 10 to the double up arrow 15, meaning a tower of 10s of height 15. So that's a pretty big number. And
yeah, I don't like this problem. It's an artificial problem. It's an artificial lower bound. That's because humans are stupid. So I don't like it. Sorry.
Okay, well, you don't like computers, probably. I mean, this is basic theory of computers. You want
I
to
know I don't like this part of computation theory.
Yeah.
I like computers a lot, but not this part.
Well, this is basic limitation. Anyway, it's a sequence, the busy beaver sequence, and we know it begins 1, 6, 21, 107, and the 5th term is unknown, and the 6th term is at least that number.
I know, but the lower bound is artificially, because humans are stupid. It's probably not realistic. So that's why.
Yeah, I agree.
Yeah.
I agree. It's not real. It's just a lower bound.
Yeah, so I don't think it's fair to compete it with the other ones. Okay.
Okay.
It's fine. We beat it anyway, right? We get a better number than this.
Yeah, we're going to get a
lower
better
bound.
number. Yeah, but not from a Turing machine with 6 states.
Right.
So anyway, that's not the biggest number, because in the next section, talking about Kaprekar's junction numbers, we get a lower bound of 10 to the, we get a sequence. It's A6064, which grows like 10 to the double up arrow log n. So it's a tower of 10s of height log n, log base 2 of n. And so this is the next section, Kaprekar's junction numbers, joint work with Max Alexeyev. In fact, looking over this, he did most of the work, but it's a nice problem anyway. So it goes back to Kaprekar. Kaprekar, I don't know if you know the name, and I can't see it because it's covered up here by your pictures. Anyway, Dattatreya Ramchandra Kaprekar, 1905 to whatever is there, I can't read it. He was a pretty famous recreational mathematician in India, and he corresponded with many people, especially Martin Gardner, many other people, looking at nice problems about sums of digits and things. And here's a question that he liked a lot, and it's an appealing question. So S, look at the sum of the digits of V, call that S of V, and add that to V. So V plus S of V, number plus the sum of digits, is little f of V. And capital F of U is the number of V's which end up at U. So U is a target. We want to find a V such that V plus S of V is equal to U. And these are called generators of U. So for example, F of 100 is 100 plus the sum of its digits is 101. F of 91 is 91. The sum of its digits is 10. So again, that gives 101. So capital F of 101 is at least 2, and it's actually 2. And it's what's more, it's the smallest decimal number that has 2 inverses, 2 generators, 101. Well, so Kaprekar wrote quite a lot of papers about the numbers that don't have any generators. He calls them the self numbers, sequence 3052, one of the old sequences. And there they are. And he calls numbers that have at least 2 generators junction numbers, because the operation brings together two arrows that end up on the same number. And so Max, Alexeyev, and I have been looking at this actually for many, many years. And we call K of n, K in honor of Kaprekar. It's the smallest number that has n generators in whatever base you're working in. So in base 10, 0 has 1 generator, just 0 itself. 101 has 2 generators, as I showed you here. I didn't prove that there are no more, but there aren't any more. And K of 3, the smallest number with 3 generators, Kaprekar found in the early 1960s, 10 to the 13 plus 1. Now, in those days, that was pretty impressive. Nowadays, you can check that directly, but it's quite impressive what they did then. Kaprekar himself found 10 to the 13 plus 1. And here are the 3 inverses, the 3 generators. And he conjectured that K of 4, the smallest number with 4 generators, is 10 to the 24 plus 102, which turns out to be correct. And in 1963, after that work, Narasimha Rao found what he considered to be the next few terms. He conjectured K of 5 is 10 to this number plus 102, and he gave upper bounds. I think he was too modest to guess that they were correct, but they in fact turned out to be correct for 6, 7, 8, and 16. And in fact, so this is a bit like digging up Stonehenge. And you say, how on earth could those people have moved those boulders around 5,000 years ago? How on earth did these people compute these numbers without computers? Maybe they must have had computers, but not very powerful ones. And the answer is, I think they sort of followed the same kinds of reasoning we did, but maybe they didn't have the guts or the determination or the insight to push through to find what Max Alexeyev did. They didn't have the moxie that he had. Or to put it another way, they weren't Max Alexeyev. But these numbers are all correct. And here are the first. So here's the sequence, A6064. It's the smallest number in base 10 with n generators. 0 has 1 generator, 101 has 2, and so on, 10 to the 13 plus 1. And it increases, and we have a recurrence that produces it. So in this case, a series of recurrences. K of 30, the smallest number with 30 generators, Max's program writes it out exactly. Then K of 100 is that. That's probably the biggest number you've seen in a while. It's about 10 to the double up arrow 9. We know that because K of n, we have a theorem that says K of n is 10 to the, it's a tower of height, ceiling of log 2 of n plus 2. So if n is 100, which is just under 128, the ceiling of log 2 is 7, add 2 and you get 9. So this is 10 to the double up arrow of 9. Right? I think this is pretty good. I mean, anyone can write down 10 to the double up arrow of 15, but to actually produce the number takes skill. And what we do is we give a set of recurrences for this. And the basic thing is that we have an apparently new recurrence for f of u. F of u, we remember, is the number of inverses of u, the number of generators of u in whatever base you're working in. And to explain that, let me just give you a hint. The key insight is, let's look in base 2. The smallest number in base 2 with 4 generators is 4102, which is 2 to the 12 plus a bit. And the generators, you look at them, it's 2 to the 12 plus 3, 2 to the 12 plus 4, 2 to the 12 minus 4, and 2 to the 12 minus 5. And it's easy to check in your head that that works. In base 2, 2 to the 12 plus 3, it's 1 with a lot of zeros and then 1, 1. So it's got 3, it's got weight 3. There's some of its digits in base 2. The binary weight is 3, 1 plus 2. And if you add 3 to that, you get 2 to the 12 plus 6, which is 4102. And the others are easily verified. But the point is, some of the generators are less than this power of 2, and some are bigger than this power of 2. And that is the basis for the recurrence. And let me just give you an idea of what's going on by talking about the base 2, the binary version. We want to prove that the number of generators for U is such and such. It's this. And to get there, we say, well, all right, let's express U in a canonical form, a nice way. We write U as 2 to some power plus 1 plus k. The cutoff is 2 to the m plus 1, and then k goes from 0 to the obvious bound. So, and the theorem says, if U is generated by, is given by this formula, the canonical representation, then the set of generators, this number, are all the numbers of the form 2 to the m plus v, where v is a generator of k, plus all the numbers just below 2 to the m of the form 2 to the m minus 1 minus v, where v is a generator of m minus k minus 2. And you can check that if you take any of these numbers and apply the operation of taking number plus sum of digits, you get 2 to the m plus 1 plus k. If you took, for instance, a number in this class, 2 to the m plus v, 2 to the m plus v, the sum of its digits is s of v, which by definition is k, because it's a generator of k. So what we get is 2 to the m plus v plus 1 plus s of v. The 1 comes from the power of 2. So this gives 2 to the m plus 1 plus k, which is what we wanted. So it's easy to prove that all these numbers are generators of U. It takes proof to show that that there are no other generators, but it's true, that's part of the theorem. So that implies that f of U, the number of generators of U, is equal to the number of generators of k plus the number of generators of m minus k minus 2, which is a very useful result. That's the basic recurrence. And there's a base B analog, and you can program this in a dozen lines of power E, and it's just a very lovely thing to use. And then, for example, here's the recurrence for k of n in base 2, smallest number with n generators. It's 2 to some power, which involves earlier values of k, plus k of n over 2. I will stop there on this section and move on. There's one coming out of this. There's a version of the Tui-Morse sequence popped up when we looked at base 5. And for each base bigger than or equal to 4, we get a version of the Tui-Morse sequence. And the base 10 version, we don't understand at all. It looks like this. And the other thing is we get this theorem that says that the k of n is a tower of height about log 2 of n, log base 2 of n. Lexicographically earliest sequences. I was going to say something about this. I won't say much, but let me just say enough to get started. So LES is the class of lexicographically earliest infinite sequences of distinct positive numbers with some property. And there are a lot of them, and they're extremely interesting and of moderate difficulty. Some of great difficulty, some we can solve. And we just solved one, which is what I was going to talk about. But I probably won't say much about it. The classical example of this is the EKG sequence, where you start off with 1 and 2, and the next term is always the smallest number, which has a GCD bigger than 1 with the previous term. And you want the lexicographically earliest sequence with that property. And there are a lot. I have a page or two of them, and there are some mysteries, many mysteries. And the one that we succeeded in analyzing this summer is the binary 2-up sequence. And this is joint work with Michael de Vlieger, Thomas Scheuler, Remy Siegrist, and Walter Trump. And the paper is just finished. It's just appeared on the archive. And the definition is, I have to move these pictures. I can't read what I've written there. I'll put you down here. Okay. So the binary 2-up sequence, it's the lexicographically earliest sequence of distinct non-negative numbers such that the nth term is perpendicular in the sense of having no ones in the binary representation with the following n terms. We define perpendicular to mean that the binary representations are disjoint. 9 is 1001, and that's perpendicular to 110. Right? That's what we want. And the rule is the nth term has to be perpendicular to the following n terms in this sense. And there's a picture of the computation of the first 18 terms. And all right, and it goes up 2 steps at a time. That's why it's called a 2-step the 2-up sequence. It's not related to the Australian gambling game of 2-up. And I didn't really understand this sequence until I did some experimental mathematics. I made a large piece of paper where I computed about 200 terms. There's the top of the piece of paper is another section of the piece of paper. And to show it, I put it on a door. It's normally kept as a scroll, but it's a meter-long piece of paper. And
So you did it by hand?
Yes, of course.
Wow.
Anyway, and then that led to a decomposition. Remy Siegrist I noticed that it decomposed into blocks. He noticed that you could decompose it into smaller blocks, which we've called atoms. And so there's the sequence decomposes into atoms. And the main theorem is that the sequence is the limit of the word S. These are atoms of length 4 or 5 or 6 or 8. So we've got 5 kinds of atoms, really only 4 kinds. And we define a word R of k to be a string of atoms like that. And then the limit, the theorem is that the sequence is the limit of this word as k increases. And one of the big questions was to prove that every number in the sequence is either is either 0 or a power of 2 or the sum of 2 powers of 2. And that's proved fairly difficult to prove, but it's now a corollary of our theorem. And we can also say essentially what every term in the sequence is. And I have to click that first. And then there's a number theory version where instead of saying the binary representations are disjoint, we could say, replace that by saying relatively prime. And this gives us a 2-up, the number theory version of the 2-up sequence. And the conjecture there is that not that every number is the sum of at most 2 powers of 2. Here the conjecture is that the sum of every number, that every number is the product of at most 2 primes. And somehow that has not been easy to prove yet. Okay, and then there were various things I didn't have time to talk about. I'm going to move the photographs out of the way so I can see that. All right, there are various things. I think we can put these slides on the web so I don't have to go through them. There's some very nice things there. And then, right, yes. And then here are some sequences where we need more terms badly by one method or another, either finding a formula or relating it to an existing sequence, since we have 350,000 sequences in the OAIS. If we looked at all of their cousins, we might be able to identify these. Or maybe you have some clever ideas for using artificial intelligence to find formulas. Here are some examples to test your skill. It would be very nice to have formulas. And you could look up in the OAIS for sentences that say, it would be nice to have a formula, things like that. And I'll end up by showing you the weirdest graph of the year. It's sequence 357082, thanks to Scott Shannon. It's the weirdest thing I've seen in a long time. That's 20,000 terms. And here is 70,000 terms. I'll stop there. Any questions?
Please thank the speaker. Okay, question 1. What is this, Neil? What am I looking at?
It's a lexicographically earliest sequence with a certain condition. I'll let you look it up. It's you have to look it up. Isn't that wonderful?
It is pretty scary.
Yeah.
Do we have any other questions for Neil?
A comment. By formula, you mean an efficient algorithm, right?
Oh, anything. No, I think there's probably efficient algorithm. Okay, yes. Yeah.
For the sequences that we need formulas, has anyone just sat down and tried to do the very dumb thing, run it through GFun or something like that to try and guess a formula?
Yeah,
or,
yeah, of course. I ran them all through Superseeker.
Yeah, through Superseeker.
It includes
well,
GFun and Rata and Guess and several other things.
Okay, so
Yeah,
that
but
actually
it-
requires something hard.
It does many transformations on the sequence and looks up all the transform versions in the OAIS. It does about 125 things to the sequence.
No, but the GCD and the prime numbers, they are very unpredictable. So this is not so easy, probably.
Yeah, yeah. Well, as long as it's related to another sequence, that's fine.
Yeah.
Neil, one of the earlier things that you showed about Z of n being A plus B over GCD of AB plus the GCD.
Yes.
Is
yes.
that, you mentioned that several sequences are part of that family.
Yeah.
Is that also something that Superseeker now knows about?
No, no, I wish it did. No.
Okay.
No, I think that's hard.
Fair enough.
I mean, you could do it. You could pick your favorite sequence and compare it with all the sequences. I wish someone would do that, but Superseeker doesn't do it at present.
Wait, well, maybe I didn't understand. What was the question about
question is,
Superseeker understand?
Can Superseeker look for a cousin of a sequence, meaning that by adding some elementary sequence to your sequence, we get a known sequence? Like that thing about the sum over products of relatively prime numbers between 1 and n.
Okay, I see. Okay, do we have any other questions for Neil? No, well, please, let's thank Neil again for giving us a wonderful talk. Okay, we'll wrap up here for the week, and we'll be back not next week, but the following week with a new talk at the experimental seminar. So thanks everyone for coming out.
And I'll be on for a few minutes if anyone has